Right, this is an AQA exam paper. It's for the combined science. It's the higher tier physics, paper 1 from May 2018. Take you about 1 hour 15 minutes to get through this, and it's 70 marks. We'll do it quicker than that though. Right, figure 1 shows 2 models of the atom, and you just got to write the labels in, choose from the box. So that's your plum pudding model. So that whole thing there was representing the atom, and this thing is pointing at something that's negative, which is the electron. Over here you've got your nuclear model, so that's pointing at the nucleus, and this here is an orbit of an electron. Next question. Explain why the total positive charge in every atom of an element is always the same. So you should know that the positive charge comes from protons, from inside atoms. Every atom of an element has the same number of protons, so that is why they've got the same total positive charge. Part 3. The results from the alpha particle scattering experiment led to the nuclear model. Alpha particles were fired at a thin film of gold at a speed of 7% of the speed of light. Determine the speed of the alpha particles, and it tells you what the speed of light is. So if we take that speed of light and divide it by 100, that'll tell us what 1% would be. Now we want 7%, so multiply it by 7, and that gives you 7% of the original speed. Part 4. Figure 2 shows 2 atoms represented as solid spheres, hydrogen and magnesium. A hydrogen atom has a radius of 2.5 times 10 to the minus 11 meters. Determine the radius of a magnesium atom. So the easiest way of doing it, that would be the radius of the hydrogen. If we call that x and we measure that with a ruler, and then if we go to the centre of the magnesium and we'll call that distance y, and we'll measure that, the ratio of x to y, just say that was 0.5 centimetres when you measured it with your ruler, and that was 3 centimetres, so that would be a ratio of 1 to 6. So basically the radius of the magnesium is going to be 6 times bigger than the radius of the hydrogen, as I've said there. So just take the radius of the hydrogen, multiply it by 6, and there's your radius of the magnesium. So make sure you take a ruler in on the day. If you haven't got a ruler, I guess you're just guessing. See how long that is, see how many times that fits in. So it did actually fit in 6 times. So using that crude method, I could work out it was still a ratio of 1 to 6-ish. And they probably would accept a range of answers. Question 2. The student wanted to determine the density of the irregular shaped object shown in figure 3. So irregular just means it's a very odd shape. Part 1. Plan an experiment that would allow the student to determine the density of the object. So I've got a nice video that'll explain how to do this. Click the link. But basically, to get the density, we need to find the mass and divide it by the volume. To measure the mass of the object, use a mass.pan balance. Measure the volume of the object, use a displacement canister and a measuring cylinder. So I've explained here how to use a displacement canister. So for each one of these bullet points, you're probably going to get a mark. So just putting that up there might get you the 6, but just in case. So you take the displacement canister and fill it with water level to the spout. So you can see the spouts there. So fill it up with water to that bit there. And place your measuring cylinder next to it. You've got this object here. So place your object into the canister and collect the displaced water from the spout in the measuring cylinder. So as that object goes down, the level of water will come up and the water will dribble out the spout. So then you catch all that water in the measuring cylinder. And the volume of the displaced water will equal the volume of your object. Part 2. Another student did a similar experiment. He determined the density of 5 common plastic materials. So there they are. Complete figure 4, which is a bar chart. You should write the correct scale on the y-axis, draw the bars for polyester, polystyrene and PVC. So they've already put the acrylic and the nylon on. So acrylic is 1200, nylon is 1000. Nylon goes up to that line there, so that line there is obviously 1000. So that's obviously 0, and then you've got 500, 1000, and then that'll be 1500. If acrylic is 1200, yeah, so every one of these is 50. So now we need to put the polyester in, so that's 1380. So there's 1000. Actually, I've done that one wrong there. That would need to go up an extra bar. So that would be 1250. That would be 1300. That would be 1350. So this here should come up a little bit more up to there. Polystyrene is 1040. So that should be just underneath that square. And this one here, the PVC, is 1100. So that's easy, just 2 little squares up above that dark line there. Part 3. The student is given a piece of different plastic material. The student determined the density of the material 3 times. Determine the uncertainty in the student's results. So uncertainty, take the largest value and subtract the smallest value and then divide it by 2. So the largest value is 1120, take away 960, divided by 2, and it comes out as 80 kilograms per metre cubed. Question 3. Figure 5 shows a diver. The diver is using a canister of compressed air so that he can breathe underwater. Which 2 sentences describe the movement of the air particles in the canister? Well, it's a gas, and gas always moves in a random direction, and they'll have a range of different speeds. Some molecules will be faster than others. Part 2. The temperature of the air inside the canister increases. What happens to the movement of the air particles? Well, the average speed or the kinetic energy of the particles would increase. If the temperature goes up, they've got more energy, you see, so they move faster. Part 3. It could be dangerous if the temperature of the air inside the canister increased by a large amount. Explain why. Okay, as the temperature increases, the pressure increases, and the canister could explode. A canister of air was tested to find out how the pressure changed when it was used by a diver. Air was allowed to escape from the canister. The pressure of the air in the canister was recorded every 5 minutes for 80 minutes. Figure 6 shows the results. So there's your graph going down over a time of 80 minutes, and that's the pressure. Estimate the atmospheric pressure. So eventually, as I've put here, eventually the pressure inside the canister will equal the pressure outside the canister, which is the atmospheric pressure, which is basically the pressure of the atmosphere. So what does it eventually get down to? This value here. What is this value? Reading from the graph, that's 0.1. That's your atmospheric pressure there. Ignore anything in blue for now. Part 5. Divers can safely stay underwater until the pressure of the air in the canister has reduced to 25% of its original value. Determine the maximum time the diver can stay underwater. Okay, so 25% pressure. If you take the original pressure and divide it by 100 to get 1%, and then multiply it by 25 to get 25%, just like we did for the previous question to do with 7%. So the original pressure, we can get that from the graph. So that's 2.25 megapascals. And then multiply that by 25 over 100. So 25% pressure is this, 0.5625 megapascals. So if we use the graph to see how long it takes for the pressure to fall to that value. So there we go, let's come down the graph until we get to 0.5625. Read off from the graph, come down here, and it's 27 minutes. So it's took 27 minutes for the pressure to drop from 2.25 down to 0.5625, 25%. Part 6. What happens to the volume of the air when it's released from the canister? Well, the volume would increase, and that's because the pressure would decrease. So you've basically opened the canister, it was 0.5, atmospheric pressure is 0.1. So the pressure's decreased to 0.1, so that means that the volume would be able to expand, the volume would increase. Question 4. The Chernobyl disaster was a nuclear accident that happened in 1986. Radioactive isotopes were released into the environment. The radioactive isotopes emitted alpha, beta and gamma radiation. What is an alpha particle? So I've wrote it here. Remember, this top number is the mass number, this bottom number tells you the charge, and that is just the symbol. So this is the symbol for alpha. It's got a mass of 4 and a charge of 2. So 2 charged particles and 2 neutral particles. The charged particles are your protons and the neutral particles are the neutrons, so that's correct. And neutrons have got a mass of 1 and protons have got a mass of 1. So I've got 2 of them and 2 of them, so that's a mass of 4. So it's definitely that one. Which statement about beta radiation is true? Okay, so it's got no mass and it's got a charge of -1. So when you read through them all, it is the type of radiation with a negative charge. That's correct. So remember, beta is a fast moving electron, but it's not as fast as gamma. Part 3. Which statement about gamma radiation is true? So the only one that's true is this bottom one here. It has a very long range in air. So I've just corrected them there. So gamma's got a high frequency, not a low one. It's got 0 charge and it's got 0 mass. Part 4. Table 3 shows the half-lives of 2 of the radioactive isotopes that contaminated the environment. A soil sample was taken from the area around Chernobyl in 1986, so the time of the disaster. The soil sample was contaminated with equal amounts of cesium-137 and iodine-131. Explain how the risk linked to each isotope has changed between 1986 and 2018. Both isotopes emit the same type of radiation. Now you can see cesium's got a half-life of 30 years and iodine's got a half-life of 8 days. So it's been 32 years since the disaster. Now, cesium has a long half-life, so its activity is still high, so it'll still have a high risk. And since it's been 32 years, there's only been one half-life has passed, so the activity now is roughly half of what it was back then. However, iodine has got a short half-life, 8 days, so its activity has decreased by a large amount, so its risk is very low. And basically, I haven't worked it out, but there'd be many half-lives have passed, so the activity is halved many times. Part 5. Determine the year when the activity of the cesium-137 in the soil sample will be 1/32nd or 1/32th of its original value. So if we've got 100% or a full fraction at first, then every half-life you're going to have half of what you had. So one half-life, I'll have half. Another half-life, I'll have a quarter. My third half-life, I'll have another half, which is an eighth. Then I'll have half of an eighth, which is a 16th. Then I'll have half of a 16th, which is a 32th, a 32nd, whatever you want to see it. So that's basically been 5 half-lives. Now, a half-life of cesium told us up here was 30 years. So we've had 5 half-lives, each half-life's 30 years, so that's 150 years will pass before the radioactivity is 1/32th. So the original disaster happened in 1986. So if we add 150 years onto 1986, that gives us the year 2136. So that'll be the year when there's only a 32nd of its original value left. Next question. Figure 7 shows cavity wall insulation being installed in the wall of a house. Explain how the wall reduces unwanted energy transfers. So when it comes to insulation, the wall needs to be nice and thick, really. So you've got a nice thick layer of insulation. Insulation's got a low thermal conductivity, so it reduces the energy transfer by conduction. Don't need to talk about convection and radiation in this case, it's only worth 3 marks. Part 2. The cavity insulation was tested. The heating inside the house was switched off. The temperature inside the house was measured every 20 minutes for 2 hours after switching it off. So there's your time, and there's the temperature slowly decreasing. Determine the temperature inside the house after 30 minutes. So they've gave you what the temperature was at 20 minutes and at 40 minutes. So that temperature is dropping over 20 minutes. It's gone from 20.8 down to 17.4. So it's changed by 3.4 degrees Celsius in the 20 minutes, from 20 minutes to 40 minutes. So if we just assume that the temperature dropped from 20 minutes to 30 minutes, well, so just over 10 minutes, that'll be half of what it dropped over 20 minutes. So half of 3.4 is only 1.7. So the temperature drop at 30 minutes will be the temperature at 20 minutes, so this temperature here, and then take away 1.7 degrees C. So it should have dropped down to 19.1. Let's just have a look. So in a 20-minute period, it's dropped by 3.4 degrees C. So we just have to assume that it's a linear decrease in temperature. So we want the temperature that's halfway between these two temperatures, and that'll be halfway between these two times. So that'll be 30 minutes, which is what the question wanted. What's the temperature after 30 minutes? So it's going to be about 19.1 degrees C. Figure 8 shows the gas boiler used to heat the house. Describe how different energy stores are changed by the boiler. So you've got some fuel being put in and getting burnt. That'll create heat, which is turning cold water into hot water, and that heats the air. So chemical energy store in the fuel is going to decrease because you're burning the fuel, and thermal energy store in the water is going to increase because the water's getting hot, and that heat is getting passed on to the air. So thermal energy store in the air will increase. And I keep on saying energy stores because that's what they say. Describe how different energy stores. Part 4. To heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. Write any equation that you use. So a megajoule is a million joules. The equation we'll use is power equals energy transferred over time. So there's your energy transferred in joules. Convert your time into seconds. So 10 minutes times by 60 seconds per minute. And the answer comes out as 25,000 watts. The original units were joules per second, but remember 1 joule per second is 1 watt. Question 6. A student built a circuit using filament lamps. Sketch a current potential difference graph for a filament lamp on figure 9. Well, a filament lamp is the same as a bulb, or as I like to call it, a spulb, because that helps you to remember that the shape is an S shape, spulb. Now, it's only an S shape, mind, if it's got both the positive direction on the graph and the negative direction. Okay, this negative direction is a mirror image of the positive direction. Figure 10 shows the circuit with 2 identical filament lamps. Compare the currents I1, I2 and I3. Okay, well, if they are 2 identical filament lamps, that means that the resistance along these paths are going to be identical. So that means that the current along these paths are going to be identical. So I2 is going to be the same size as I3. And what we also know from Kirchhoff's law is that this current here, the current into a junction, equals the current out of the junction. So I1 is going to equal I2 plus I3. And that's what we've got there. And since this path here is identical to this path here, we know that I2 is going to be half of I1, and also I3 will also be half of I1, because the current is split perfectly in half in this example. Question 3. Calculate the charge that flows through the cell in 1 minute. Each filament lamp has a power of 3 watts and a resistance of 12 ohms. Write any equations that you use and give the unit. So, first of all, find out what it is that you need. So calculate the charge. So charge is our target. Through the cell in 1 minute. Okay, so we've got the time. Let's convert it into seconds. We've got a power, so write P next to that. And we've got a resistance, so write R next to that. Now we know that we want Q, so we're probably going to need Q equals I times by T. Now I've got a T, but I don't have an I. Okay, so I have got a power and a resistance though. So can I relate these two things to the current? Yes, I can, using this equation. So P equals I squared R. Let's rearrange that to make I the target, but I don't want I squared, I want I. So let's square root both sides, and what we get is this. I equals the square root of the power divided by the resistance. Now, if we use the power of the lamp and the resistance of the lamp, we're going to get the current through a lamp, as shown here. So we'll end up working out I2. And remember, I2 is the same as I3. So once we've worked out I2, we know what I3 is as well. So let's pop the numbers in, and it turns out that the current coming through here, I2, is 0.5 amps. So that means that the current through here is also 0.5 amps. Now the original question wants to know the charge through the cell. So we need to know the current through the cell. So that's I1. So I1, remember from the last question, is I2 plus I3. So we'll add that to that, and it comes out as 1 amp of current going through the cell. So now that we know that, to work out the charge through the cell, let's just take the current through the cell multiplied by the time. So 1 amp times by 60 seconds, and that comes out as 60 coulombs. Charge is always measured in coulombs. Make sure you put your answer up here where they expect it. And part 4, this is the last question on the paper. It's another 6 marker. The student builds a different circuit. Figure 11 shows the circuit. Explain how the readings on both meters change when the environmental conditions change. So remember, environmental conditions can be things like pressure, temperature, light intensity. In this case, we're using an LDR, which is a light-dependent resistor, so we're interested in the environmental condition known as light intensity, so how light or dark it is. So, explain how the readings on both meters, so the voltmeter and ammeter, change when the environmental conditions change. So, well, the first thing is, you've got to know that the resistance of an LDR changes when the light intensity changes. So we've successfully identified which environmental condition is important here. And if the light intensity increases, do you know that the resistance of the LDR decreases? That's important for you to know. So if this resistance is going to decrease, since this voltmeter is across the LDR, if the resistance goes down, that means that the voltage is going to go down. So the voltmeter reading across the LDR will decrease. Now remember, the voltage on the fixed resistor would increase since voltage is being shared when the components are in series. So if this voltage goes down, then that voltage would go up. They're not really interested in that because they're only interested in what's happening on these meter readings. But just in case they ask you next time, these two components are in series. So whatever this voltage is here, just say it was 12 volts. Just say you had 6 volts on there and 6 volts on there at first. But now let's just say that this voltage goes down to 2 volts. This voltage here would have to go up to 10 volts. So 10 plus 2 would still equal you 12. So that's what these statements here are about. Now let's get back on track and talk about the ammeter. So the reading on the ammeter would increase because the current would increase. And that's due to the resistance of the LDR decreasing, which would make the resistance of the total circuit smaller. Yep, so the resistance of this is going to get less. So even though the resistance of that stays the same, because this is less, that means the resistance of the total circuit is going to be less. And if the resistance is smaller, that means it's easier for the current to flow. So that means the current is going to get bigger. Okie dokie. So I've absolutely bashed that. We've powered our way through that. I hope it was useful for you. So whether you do Excel or whether you do AQA, as long as you do both papers 1 and 2, you'll cover everything that you need for your particular exam board. Okay, I hope that's useful. Make sure you've subscribed to the channel, hit the like button, and I'll see you in the next one. Bye for now. Work hard and be nice.